for giving me this opportunity to speak. Ian already described a number of material problems. There are a lot of things we don't know. What I'm going to talk about is how we can use advanced technique such as the Synchrotron X-ray technique to answer some of the questions. So since today is a celebration of the CP-1, so we first look at the past achievement. In fact, nuclear technology and high-performance material are two of the greatest achievements in the 20th century. And the combination of these two greatest achievements actually create an even better product, which is nuclear power. It's a reliable and sustainable and safe energy source. So if we look at the CP-1, it is really a pile of graphite with uranium. But if we look at today's power plant, it actually have a wide range of materials that employ in a nuclear reactor. So the success of nuclear energy definitely has to rely on the very good material that can be used in the reactor environment. So although the material have been performed satisfactorily in a nuclear power plant, but we still have a number of material challenges we have to address nowadays. First of all, the nuclear power plant asking for license renewal, so the lifetime is being extended from 40 years to 60 years, or even longer, 80 years. So the material that we'll put in the reactor may not be the same, actually will not be the same. It will age and will change, so we need to understand how material will age and degrade for long term, and so we can predict how the structure and component can safely run for a long time. If we talk about the advanced reactor, of course the material challenge are quite different because advanced reactor will have very different operating environment. For example, the sodium fast reactor, now we need to find the cladding material that can tolerate much higher damage dose. For a light water reactor, maybe 100 dPa is good enough, but for advanced reactor, we probably need material that can stand several hundred dPa damage. And also the high temperature reactor, we don't have a right material that can survive at very high temperature for a very long time. And of course, when we talk about molten salt reactor, do we have a material that can survive in a very corrosive environment? We don't know. And also, in order to have any new material to be employed in a reactor, it must be qualified. And the qualification of new material has been a really long process. So we need to accelerate the process to be able to use a new material in the reactor. After Fukushima, so there's other things we probably haven't addressed enough. Now we need to think about more when we develop new materials, because the material not only has to perform well in operating condition, but also has to be able to perform in an accident condition. So with all these number of material challenge, how we are going to address that? In fact, the material science advance can really help us to do a lot of things which was not done before. For example, the advanced material, now we can design radiation-resistant material. We can introduce nanostructure to increase the radiation resistance. For example, oxide dispersion strengthens steel is considered for cladding application. We also can design heat-resistant advanced material. For example, alloy 709, which is advanced stainless steel that has been actively developed under advanced technology program in NE. Of course, we also need to develop next generation accident-tolerant fuel, accident-tolerant cladding materials such as silicon carbide and maybe the coating on zirconium. There are also a number of other material design concepts, for example, high entropy alloy, multi-layers. But what I really want to focus on in this talk is how we can utilize all these new characterization tools, because now we have very different tools we didn't have before, so we can do the experiment very differently. Those new tools can give us a much better time and spatial resolution, so we can see the things we didn't see before. And also now we can visualize microstructure in 3D. And also a lot of experiments now they can do in situ. So we can monitor how material change in different conditions. Of course, a computational tool, particularly when it's combined with in situ experiment, can really help us not only design the material and also to understand the degradation mechanism better and to better predict the surface lifetime. In this talk, I will primarily focus on synchrotron X-rays, and there are a lot of new experiments that can be done with synchrotron X-ray technique. For example, the experiment can be done in situ, and with the synchrotron X-ray, we can build very complex sample environment. This is particularly important and useful for studying nuclear material because we want to simulate a reactor environment which has to involve loading, and, temperature, and corrosive environment. And also, if we want to see how material processing affects the material, having this in situ capability is also very important. Another very good advantage of the synchrotron is 3D characterization. So unlike other 3D characterization tools, X-ray really allow us not just to see the surface, but also see through the interior. For nuclear material, this is, we know the material is not uniform, so it's important we'll be able to map the inhomogeneous microstructure or chemistry or mechanical state. And also because X-ray is non-destructive, so we can really use this technique for radioactive material, which is a particular challenge for our community to deal with. And also, Ian talked about how important to bridge different scale of the materials so we can understand material better. Because material problem is generic multi-scale, and for radiation damage, when things happen in a picosecond and continue to evolve until many years, so it's very important we not only understand the atomic scale, the individual event, and we also need to be able to link those atomic scale events to mesoscale and eventually to macroscale, so we'll be able to understand how microstructure and property connect together. This is just to give you an example how we can do in situ multi-scaled experiment using high-energy X-rays. I really think high-energy X-ray has a particular advantage when we look at the nuclear material because of a deep penetration. And also because high-energy X-ray allow us to look at a large size sample. So when we measure the sample, we can measure the bulk property, which is very important. And for study nuclear fuel, because the fuel is a heavy element, so you also need to have a high-energy X-ray. And so this is show you the example. So with a high-energy X-ray, nowadays we can do the typical large-scale mechanical testing in the beamline. At the same time, to use X-ray to measure the microstructure. And using different detector, we can not only measure one size of the scale, we can measure multi-scale. For example, we can measure, in this case, measure the lattice parameter, lattice strain, and also using small angle scattering technique to look at the nano-sized voids or multi-phases. And also going to mesoscale, you can look at individual grain or subgrain and see what happened there. And in one single experiment, you can get information from nanoscale to mesoscale and also up to macroscale to directly link all these microstructure feature to the materials property, which is unthinkable before. So this is important capability that's enabled by high-energy X-ray. I'll just give you a few examples on what we can learn from this kind of experiment. So this is an example about 316 stainless steel. 316 stainless steel we know is broadly used in reactors. Almost any reactor uses material. So one of the problems of this stainless steel, we know after radiation, material become very hard and become yeah, I'm sorry, become very hard, but also become very brittle. So the embrittlement is always something we worry about for structural material. As you can see, after radiation, the elongation of material is only 1 or 2%. But in fact, if we test a different stainless steel, this is again 316. Was released to the very similar condition, but if you look at this, another 316, the ductility actually can go almost up to 30%. So what happened? The same, it's all this 316. How come one 316 has such better ductility property than another one? And then we did in situ experiment doing tensile test with X-rays, and we have very good answer for this problem. So during the tensile test, we used an X-ray to scan the specimen gauge. We found the depression pattern along the specimen gauge. Sorry. Yeah, here it is. I don't know if the movie shows. Okay, so it's actually the diffraction data along the specimen gauge is very different. So we realize actually the deformation is not happening uniformly like in the non-radius material. The deformation actually happens as one end of the specimen and then start to wipe out the gauge. And once the deformation band propagates, it actually triggers the phase transformation. So austenite actually become martensite. And we know martensite is very hard. That's why the material doesn't have this typical early onset of plastic instability. That's why this material has much longer elongation. So when we talk about advanced material, we often don't think about 316. But in fact, just with a minor tuning of the chemistry or processing, we probably can get some much different performance of the material, of the traditional material. So this is another example. This is basically use a 3D characterization technique, so-called high-energy X-ray microscopy, to look at the deformation microstructure, how the radiation affects the deformation. Because we know in our community, we often use the TEM to study radiation defect. We have a very good understanding of the defect generation. We also have a lot of mechanical testing data, so we understand the property. But it's very difficult to put these two pieces of information together because we really don't have a lot of information at the intermediate scale. So this high-energy microscopy technique actually now allow us to look at individual grains or subgrains. So what you're seeing here is a neutron-radiated iron chrome alloy. So before radiation, we can map the grain in 3D. And after radiation, when we masked again, the grain didn't change. But during deformation, the grain actually split into the subgrain. But if we compare the subgrain, the map between the non-radiated sample and radiated sample, we do see the difference. In the radiated sample, we see there's some large subgrain coexist with the small subgrains. But actually, in the non-radiated sample, you only see small subgrains. So what does that mean? And also, we measure the strain in each individual subgrain. It's actually quite interesting. So this is the residual strain distribution in the non-radiated sample. If we radiate, the residual strain distribution becomes much broad. And then if we deform, the residual strain distribution becomes even broader in the non-radiated sample. But if we have radiation and deformation, interestingly, it looks just like a non-radiated sample. So this technique basically tells us when we look at the subgrain formation, radiation defect probably play one role. But when we look at the residual strain distribution, radiation and deformation defect probably play a very similar role. This is an example of stress corrosion cracking. Stress corrosion cracking is probably one of the most important problems for nuclear industry. But it also happened to be one of the most difficult problems for material scientists to study. because there's so many processes happen at the same time. It involves corrosion, involves the stress, so it's very difficult to pin down which process dominant. It's also difficult study is because this is a cracking problem that happens in a component, but we have to understand the atomic scale mechanism. So actually, high-energy X-ray, again, turns out to be a very useful technique to look at this problem. So this experiment basically uses two 3D technique in combination with the in situ experiment. So using X-ray tomography during in situ stress corrosion cracking experiment, you can capture the crack path. And after the test, you can use diffraction contrast tomography to map the grain to show the grain boundary. So when you combine these two sets of data, you see exactly which grain boundary has a crack, which grain boundary doesn't. So that tells you which grain boundary are more resistant to stress corrosion cracking. So that's really a very important information for doing grain boundary engineering to improve the resistance of the material to stress corrosion cracking. So talking about nuclear fuel, it's a very different problem because this is actually the experiment researchers want to look at the nuclear fuel melting process. In order to do this experiment, you need to heat the fuel to 3,000 degrees C. Now to say you also want to watch how the fuel evolves during this melting process. It's an extremely difficult experiment. But it's made possible, again, this is experiment done as APS. Researcher built this complex sample environment and being able to use a high-energy X-ray to do diffraction experiment. And this diffraction experiment will tell us the atomic configuration of the uranium oxygen distribution in both solid and liquid. So this finding is very important to understand the nuclear fuel melting process. Talk about advanced manufacturing, we probably cannot ignore additive manufacturing. This has been actively pursued in many industries. So can 3D printing really a game changer for nuclear industry? Well, definitely 3D printing has a lot of advantage in terms of, it's a very quick turnaround and a low cost for making parts. And also, particularly for nuclear industry, if you have the high value and low volume parts to make, this is a nice technique to have. But maybe we haven't think too much about whether we can even use 3D printing to make the material not only meet the requirement of traditional material, but even better property. So when you get the product, you have the much better material with right-shaped components. So in order to understand additive manufacturing, the process and material better, definitely in situ characterization and X-ray technique can play an important role. And this give you an example. This is an X-ray imaging experiment to show the laser powder bed fusion. There's a two movie here. I actually don't know how to play this one. Let's see the word is right now. I have to click the two movies.
Click on the videos.
Yeah, the video. If you click both. Okay. Thank you.
No problem.
So these two videos actually show two different melting modes. One is a keyhole mode, one is the conduction mode. So from this movie, you get a very straightforward information how the different melting mode will affect the materials and potentially have the effects on porosity. So you have seen some nice example how synchrotron X-ray can help us to understand the material better. And actually, there's a lot of new techniques that's being developed and to be developed, give us a better opportunity. This is just show one example, the APS upgrade. The beam will become more coherent and the intensity will be higher. So there will be new technique that will be available. This is a high energy X-ray microscope beamline to be built. So with this new beamline, we'll be able to not only do diffraction and scattering, this kind of experiment, there will also a lot more imaging capability will become available to us. And with this new capability, we have better chance to look at the multi-scale feature in a single experiment. And also because this is a very long beamline, that will go outside the APS in a separate building. So we also have the opportunity to build radioactive material laboratories, so we can look at radioactive material using those new technique. Well, dealing with radioactive material is always a headache. But if we look at the other technology, particularly the robot, this small movie show how robot can really help us to handle radioactive material in the future. So not only the advanced characterization technique can also can help us, we also need to think about other techniques that makes our materials study easier. So in the previous example, when I talk about in situ experiment, probably you'll notice there's one environmental factor missing, which is radiation. We know once we put material in the reactor, the damage will happen in a picosecond or even shorter time. So being able to see how radiation damaged material generating defect is very important. So at Argonne, we have this facility called IV antenna. Basically, this is a TEM that's the interface with the ion accelerator. So we can use a heavy ion to generate radiation damage that's similar to neutron damage. So we can watch how defects generated and evolved. So those little black dot are 1 or 2 nanometer dislocation loop. And this movie actually shows when the loop become larger, how they can even grow into a different configuration and different size of defect. So it's important to have this kind of a capability. So the question the community probably want to think about it, should we also have this similar capability, adding accelerator to do in situ radiation experiment with X-ray technique? Argonne actually has a proposal called Extreme Beamline XMAT proposal. So basically, to use both X-ray technique and ion radiation beam to damage the material at the same time to observe it. So to conclude my talk, certainly there's a very impressive achievement in the past in terms of nuclear technology and also developing materials that makes the nuclear power possible. And nowadays, there's a lot of new techniques, characterization technique, computational tools that can help us to understand material much better, and we can do a lot of experiments that was unthinkable before. So we should take those opportunities and to think about, what will be the future experiment we can do, how we can use those advanced tools to accelerate material development to make the nuclear power the future energy source. So I want to thank a number of people I work with at Argonne and also in other institutions, and also several people who contribute to this talk. One person I want to mention in particular, which is John Ulmer, sitting right there. So over the years, we two worked very close together on this project. In fact, without John's constant and persistent support, I don't think we'll get to where we are. So I want to say thank you to him, and also want to thank the funding source, LDRD, and also Office of Nuclear Energy, to make this happen. Thank you very much.